So these are our tangent line approximations. You will also see them as linear approximations. So basically the basis of this, if I have some sort of graph, yes, and I find my derivative at a point, yes, can we create a tangent line that goes through that point? Yes, right? So it's going to kind of, remember, go through that point like that. Yes? So let's say that this value is at A. You with me? Basically what a tangent line approximation or linear approximation does is then I can say, okay, well maybe I don't have a ton of information about my blue function. So what I can do instead is say I want to find this number that's really, really close to A, okay? But I don't have enough information to actually find the actual value. So what I can do instead is find my tangent line, okay, equation, and then use that equation to approximate that point. Because it's close enough that a tangent line is going to be pretty close to it for anything that's near that point. Does that make sense? So it's going to be a fairly good approximation. Now, so if my A value was at 2, 2.1 is going to have a pretty close approximation. If I try to approximate 4, right, that's not going to be super great. So most of the time, we're going to approximate things that are close to it. So basically, a tangent line approximation is using the equation of the tangent line to approximate the function at a near value. Now, what is our general equation of a line in point slope form? Equals? Okay. We're all okay with that. Yes? Now, the other thing that I'm going to change is if I am using my tangent line, alright, to approximate this, what is my slope going to be? The derivative, right, at whatever my value is, which in this case we're labeling as A, right? So that means, so then what would my Y value be in function notation? If my X is A, then Y would be F of A, right? So this would be Y minus F of A equals the derivative at A times X minus A. We're all okay with that? Again, it's kind of just putting it in like a nice formula form. Okay. But then what we tend to do is, because we call this a linear approximation, we're going to label my Y as an L of X. Okay. So I have F prime of A times X minus A, and then I'm just going to add that F of A at the end. And the reason why we like this form, right, is because notice, like I said, if A is 2, right, and I'm looking for 2.1, I'm going to plug that 2.1 right there. Well, 2.1 minus 2 is pretty easy to figure out. 0.1. So it's, like, we like that form because it's pretty quick to just plug and chug from that. What questions do we have there? Okay, so let's look at some notes. So it says find the tangent line approximation of the following function at the point 0, 1. Let's do 4. X equals 0.1. So I have an f of x. What do I need to do first? Yeah, so they give me a point that we're wanting to kind of revolve that around. Yes? Agreed? Yeah. Okay, which is 0, 1. And if sometimes they might just say starting or using the x value, x equals 0, and then remember I still need a point. So I would have to plug that x value into my function to figure out what the y value is. But here they give us the whole point, so we can just take f of x. What do we get? Okay. And then what is our a value this time? Or what we're revolving it around?
Cosine x. Cosine x.
Oh yeah.
Agreed.
My fault.
No, you're fine. So, positive cosine x. So, we are using our a value again, remember, is the x value that we're using to approximate, okay? So, what x value, what point do they want us to use? 0, 1. So, my x value here, or my a value is 0. What is cosine of 0? 1. Okay, so again, our L of x. So if it's hard for you to remember the formula, you can always just remember my y minus y1, which here is 1. I'm using my derivative that we just found, which I'm going to go ahead and write it just so you can kind of see it all out together. And then I'm going to multiply that by x minus 0. Are we all okay with that?
Yeah.
Alright.
It's the same formula, we're just using the derivative.
As your slope. And we've used our derivative, right? Like we found, I've said, like find the equation of the tangent line at this point, right? So we've done this part. It's just now we're going to use that, right, to approximate something else. So then again, if I solve for y, that gives me my linear approximation, and this just becomes x, right? And then it's a 0, so I just get x plus 1. Are we all okay with that? So cosine is a good one, or cosine and sine trig functions are good ones, because like they're not usually nice, pretty numbers. And so if we didn't have a calculator handy, right? Well, 0 and 1 are going to be nice numbers that I could plug in. So this is still going to give me a fairly good estimate at what L of 0.1 is. So I'm plugging in my L of 0.1, so my x, and what do we get? 1.1. Yes? Okay. Now, we're going to check our work here in just a second to see what it looks like. But if we didn't, so like say this was a non-calculator active portion, and I wanted to know if this was an over or an underestimate, how would I figure that out? So let's go back to a graph. What's the graph of 1 plus sine of x? It's a wave, and what's happened to it? It's been shifted up by 1. Yes? And normally our sine graph starts at 0. And it goes which direction first? Up. So like something like that. Yes? So then what we have to decide is, if I draw my approximation here, right, I am using this point, right, at 0, 1 to approximate that. Yes? Agreed? So if I'm looking at point 1, where is that going to be? But very close, but where close? Above or below? It's going to be above it. which means that it's going to be an overestimate. Now, do we know what makes that an over versus an underestimate? Well, yeah. But what makes it above it versus below it? I think my other one. So like this one would have been an underestimate, right? It's not necessarily increasing or decreasing. It's the other one. Yeah. So notice that this one is concave up, right? So my linear approximation line, okay, is going to be hit it at that point, but then because it's concave up, it's going to be below it. So this one would have been an underestimate. Versus, so the right of this one, this is concave down, right? Which means that my line is going to be slightly above it. So it'll be an overestimate. So in general, so concave up means that we have an underestimate, and concave down means that we have an overestimate. Now you can always draw like a picture like this. However, sometimes it will, if it just gives you like specific values, it could say f double prime of x is greater than 0. And then you would have to know, that means concave up, so that means that it's going to be an underestimate. Okay? Now, if we actually plugged in 0.1 for our original function, so someone plugged in for the calculator for me, what would our actual value of f be? So f of 0.1 is approximately what? 1.099. Well, is 1.1 a fairly accurate, like, rounding of that? Yeah. Now, notice that if I had done something, like, way farther away, so, like, let's say we did L of 1.1 instead. What would that have been? 2.1, right? Because I would plug it back in here. Okay? So then what is f of 1.1? So plug it in for me.
1.8.
So again, I mean, it's not like an awful estimate, but it's not great either. So the further away that you get from the initial point that you use, the worse that your estimation is going to be. Does that make sense? So that's why we tend to stick with something that's fairly close. Alright? So next up, we could see it giving us like a table of values instead, but it's going to work very similarly. We actually don't have to do much like derivative math calculations. We just have to know what to plug where. So it says selected values of the derivative of the function g are given in the table. It is known that g of 4 equals 12. What is the approximation for g of 4.2? Found using the line tangent to the graph of g at x equals 4. So again, we're just using our y minus y1 equals m times x minus x1. What's the point that they give us? They don't technically give it to us as a point, but what is the point? What? 412. Alright, so that means that I have y minus 12 equals, and I'm going to have an x minus 4. Alright. And again, what acts as my slope? At what value? Yeah, so we need to know what is f, well, technically in this case it's g. What is g prime of 4?
2.2.
Yeah, so g prime of 4 is 2.2. So that's what we're going to use as our slope, which then means that we can rewrite this as L of x equals 2.2 times x minus 4 plus 12. Reallocate that. Yes? So that would be our linear approximation line. And then they ask us to approximate what? The axis to approximate what? 4.2. So I have 2.2 times 4.2 minus 4 plus 4. Well, what is 4.2 minus 4? 0.2. What is 2.2 times 0.2? 0.44. Okay, and then so plus 12 gives us 12.44. And that's our answer. Yes? Questions do we have there?
Yeah, you did say that after approximation equation, you just replace the slope with
The derivative at the point that they want you to use. So in this case it was 4, so it's the derivative at 4. Yes? And like what they could have done as well is they could have said, like, no, and then also like g double prime of 4.2 is equal to, I don't care, 0.5. So then now, do we have an over or an underestimate?
Underestimate.
It's going to be under. Because that means that our graph is what at 4.2? Concave up. So we would have an underestimate. Yes? Alright, so lastly, this says let f be a function such that the slope is given by the following, and f passes through the point 1, comma, negative 2. Use the information to find the approximation of f at x equals 1.3. So this is the last type that you could see. Do they give us a function this time, like f of x? No, right? What do they give us instead? They give us the derivative, right? Well, they also give us the original point, so that's nice. So I'm going to have y, technically plus 2, right? Because it's minus a negative 2, equals, we're going to have to find our slope here in just a second. Now, what is our slope in general? What are we using as our slope? The derivative. So this time, instead of having to take the derivative and plug in, they just give us the derivative equation, so we just have to evaluate that derivative at the point that they give us. Yes? So I have 1/2 times 1 minus 1/4 times negative 2 squared. Yes? So what do we get? I have 1/2 times 1 gives us 1/2. Negative 2 squared is 4 times a 1/4 is, so minus 1. So we get negative 1/2. So now that's going to act as our slope. We're okay with that. So now, what's our L of x?
1/2.
Negative 1/2.
Sorry.
Times?
Times x minus 1 minus 2.
Minus 2. And what do we want it to approximate? Okay. So L of 1.3. Now what is 1.3 minus 1? Okay. Now this would be a good one that probably would be on the not calculator active portion. So 1, if it's on the not calculator active portion, we could leave it right there. If it was a free response question. We don't have to find anything else. Now, if it was on a non-calculator active multiple choice question, you would have to do some simplifying. So what is 0.3 as a fraction? Okay, so I have negative 1/2 times 3/10. So what does this now give me here at the start? Negative 3/20 minus 2. So 2 would be 40/20. So we get negative 43 20th. Yep. And that'll be it. Like I said, if it was free response, we would stop here. If it was non-calculator active. Which, like, this would be one that would probably be non-calculator active. And so that's why I said it's nice if we leave it in this x minus 1 form. Because sometimes you'll see in the book they'll actually, like, distribute and simplify. I like leaving it in this form because this subtraction is usually pretty easy, again, because they're giving us a number that's close to our original x. What questions do we have there? Alright, that's all we got for today.